Greetings, ladies and gentlemen. I am Professor Dr. Valdemar Vicente Graciano Neto, Head of Insight Go Research Group and an Associate Professor at the Federal University of Goiás in Brazil. I'm going to present a paper entitled Architectural Strategy to Enhance the Availability Quality Attribute in Systems of Systems Architectures, a case study, whose first author is Mr. Alexandre Delecolle. This is the final product of an international internship in which Mr. Delecolle spent some months in Brazil under my supervision in Goiânia. Hence, this is also an achievement of an international research collaboration. Since we are in the online environment, our research group glimpses it as an opportunity to offer a more attractive presentation for our audience. It's important to highlight that, regardless of the format, we are still strict about the precision in correspondence with the paper content, the serious-mindedness of the content being communicated, and the scientific rigor about the research that was conducted and the results being reported. Our intention is to be more informative and provide you a better experience. So let's go! Multiple software-intensive systems have formed alliances called as Systems of Systems, or SoSE, to interoperate and deliver functionalities as a result of the combination of their individual capabilities. Systems of Systems are actually required to exhibit quality, that is, they are required to deliver their behaviors under a set of restrictions named as quality attributes, or QA. As a consensus, and due to its software nature, a SoSE can be built and evaluated about its quality through its associated software architecture. A SoSE software architecture comprises its constituent systems, their interaction links, the shared decisions and the rationale that triggers its building, and the description of its surrounding environment. Among the several QA, availability is particularly important for SoSE with critical nature. If we consider, for instance, a SoSE for emergency response management and it becomes unavailable, users can become exposed to risks and be helpless. Hence, availability should be strictly assured. However, assessing availability at design time can face some difficulties in regards to SoSE contexts. Since constituents are not totally known at design time, constituents can join or leave the SoSE at runtime, which turns the SoSE architecture to be dynamic, and availability of a behavior depends on the presence of specific constituents that provide the required capabilities to deliver a set of expected behaviors. And finally, most of the languages used to specify software, such as UML or SysML, do not enable to model a dynamic architecture. Once changing the entire architecture would require a redesign of the documentation every time a change occurs. Given that context, we then established the following research question. How can we design and specify architectural strategies to address the quality attribute availability in systems of systems? To answer it, we used the SoSE language to specify an architectural strategy to deal with availability at SoSE level. We relied on a model transformation to automatically generate simulation models specified in devs to assess the effectiveness of the established strategy. We ran the simulation models to observe the expected behavior and whether availability was effectively addressed at the SoSE level. We discussed our method as follows. Our research was structured in the following well-defined steps: literature review, project setting, solution development, and evaluation. From the literature review, we found that the investigation on availability in SoSE, and more broadly reliability, is not a new trend. Some authors have already used model-based development techniques, mathematical solutions, and UPDM. However, from the best of our knowledge, the evaluation of QA availability at SoSE software architecture level using SoSE, a recent language that enables modeling SoSE abstract architectures with constituents not totally known at design time and support for dynamic architectures, and a model transformation that automatically produces executable simulation of architectural models that allows the SoSE engineer to assess quality attributes still at design time, sounds as a novelty. Once the gaps were identified, we decided to contribute to the state-of-the-art by establishing an architectural strategy to deal with QA availability in SoSE. We looked for an instance of a SoSE, a smart parking, that could be specified in order to evaluate the success of our work. We proposed an adapted definition of availability for SoSE context and used the concept of replaceability to deal with availability. Replaceability consists in providing redundant functionalities and constituents so that, if a failure occurs, the availability of the SoSE is not affected. The replaceability principle states that the SoSE should offer semantically redundant but not necessarily identical functionalities in different constituent systems such that, if one fails, there is at least another one to substitute it as a backup. We realized that for SoSE contexts, availability should be rewritten as a degree to which the SoSE, as a coalition of its constituents, is capable of delivering a behavior when required. Once we established the definition, we then set up a context for our research. We specified the smart parking composed of a car, fixed sensors at parking positions, and a mobile robot that plays the role of backup. When a car arrives at the parking, it asks for a position to park to the smart parking system. Sensors at positions are used by the parking to detect what positions are available or not. The parking then responds with the location of one free position to the car. If a sensor fails and this is detected, the robot is then triggered to substitute it temporarily. We specified this SoSE in SoSE and used the model transformation conceived by Graciano, Neto et al. To automatically generate dev simulation models. We deployed them in the MS4Me environment and run the evaluation. Failures were randomized in 50% and 72 demand answer loops were executed by the simulation. At least in that scenario, we achieved an availability of 100%. However, this study has some limitations. We used only one constituent as a backup, and we assumed it is always available. If it was not, the availability would not be 100%. Several other constituents could also be added to improve the redundancy and the effectiveness of the replaceability principle. We rely on the correctness of the model transformation to produce credible simulation models that are strictly corresponding to the equivalent architectural documentation in SoSE. This threat is relieved by the fact that more than 1 million lines of functional simulation code were already generated using that model transformation in other SoSE projects, modeling flood monitoring systems and smart buildings. About the empirical nature, the randomness phi could also be varied, the scale of the SoSE could also be varied, and non-equivalent but close redundant capabilities could also be tested. These topics are for future work. This paper presented the establishment of a method to assess availability at the software architectural level of a smart parking system of systems. Availability definition was revealed and provided as a result of capabilities redundancy and replaceability. We also contributed to the characterization of what could be considered availability at SoSE level and offered an implementation solution to automatically generate DAVs simulation models from SoSE models to support the evaluation of availability at software level still at design time. Further studies can be still conducted to expand the context of this study, using more constituents as backup and testing how availability degree is influenced by the presence of non-identical but semantically close capabilities. Other possibilities to sense the environment could also be exploited, such as exploring the car's sensors to detect available positions and communicate with other drivers, or using cameras with computer vision and detection or drones to detect cars using sensors as well. We thank RTC Inc. by providing the student license for a Mass for Me environment, École Militaire Saint-Cyr by the scholarship that supported Alexandre during his internship in Brazil, and the Federal University of Goiás by offering the environment where this project was developed. This presentation is also available on YouTube. Subscribe there for more high-quality content. Thank you very much for your attention, and now we are open for questions.